All right, so theoretical versus experimental probability. Everything that we were doing yesterday and the day before is what we call theoretical probability. What it means with theoretical probability, it's what we expect to happen. It's the what should happen portion. In fact, we're going to write that down. This is the theory of what should happen. And that's a really, really big deal. So if I flip a coin, I should land on heads 50% of the time, right? Yes or no? Yeah. Okay, if I flip a coin, I should land on heads 50% of the time. I should land on tails 50% of the time. Elijah, calm down. If I roll a die, I should land on a value of 1 out of 6 times. In theory, that's what should happen. So when we talk about theoretical probability, this is the part where there is no action actually happening. We're just looking at our item. Where'd my stuff go? So I'm looking at my die and going, okay, here's a number cube, here's a die. I know that the probability of me rolling a 4 is 1 out of 6. That's something that I know. I didn't have to do anything. I didn't have to actually roll it and see if it happened. That's just a theoretical probability. So when we're finding theoretical probability, we look at the idea of the number of favorable outcomes, like how many of those specific outcomes that we're wanting, the desired event, is on our activity versus the total number of outcomes that are on our activity. Okay, so we have absolutely no action happening. I'm not having to roll this die to figure out that the theoretical probability of landing on a 4 is 1 out of 6. Okay, so let's write that as an example. Okay, we're going to roll a die. And I want the probability that I'm going to land on a 4, and that's going to equal 1 out of 6. Or if I were to flip a coin, then the probability of landing on tails is 1 out of 2. Okay, those are all in theory what will happen. Now, experimental probability is different. With experimental probability, that involves an actual experiment. Some action has to actually happen. So theoretical probability, no action. It's what we expect or what should occur. With experimental probability, there's action that is required. I physically have to perform my experiment. Okay, so action is required for there to be an experimental probability. Okay, this is what we would call what actually is happening. Okay, when we actually roll the die, how often did we land on 4? When we actually flip the coin, how often do we land on tails? Okay, so for there to be an experimental probability, there has to be more than one trial. Okay, there should be at least 2 trials in order for it to be considered an experimental probability. All right, so like I said before with our examples, if we're rolling the die and I want the probability of landing on a 4, in theory it's 1/6, but when we're talking about experimental probability, that means we have to have a number of trials performed. So I'm going to roll a die 27 trials. Okay, and then I'm going to identify that it lands on the number 4 8 times. So then my experimental probability becomes how often did the actual event occur, which in this case was 8 times, out of the total number of trials, not outcomes. Okay, so there's 27 trials. So the probability of landing on the 4 was 8 out of 27. Okay, same thing if I'm going to flip a coin. Flip a coin, 70 trials, and then it's going to land on tails 30 times. So then here, my experimental probability of landing on tails is 30 times that I got tails out of 70 times that I flipped the coin, or as we simplify it, 3 over 7. Because so often you're going to find that your experimental probability doesn't exactly mirror what your theoretical probability is. Okay? You are not guaranteed to flip a coin and land exactly half of the time on tails. It's not guaranteed to happen that way. What the probability entails is that every time you flip the coin, that coin has a half chance of landing on tails and a half chance of landing on heads. So the theoretical probability is basically the idea of what's the correct answer. Experimental probability is that process of us getting to the correct answer. Okay? Now, go ahead and flip it on over. We're taking a look here at a graph that's been provided for us of spinning a spinner. So the spinner has 3 equal sections. That's a really important thing to understand. Okay? This is what we call a uniform experiment. Uniform experiment means that every single one of your outcomes has the same probability of happening. It doesn't mean that it's 50-50. It just means that every outcome has the exact same potential for happening. So if it's equal sections, that means that there's the same number of green, same number of blue, and same number of red that can occur. Okay? So here, actually, let me grab a piece of paper real quick. I'm going to show you the difference between a uniform spinner and a non-uniform spinner. You can actually flip your paper over to the back side. And I just want you to quickly draw 2 circles. Doesn't have to be perfect. Okay? So we have 2 circles. The first circle, I want you to split it up into 3 sections. I know it doesn't look perfect, but we're going to pretend like it's perfect. Okay? The next one, I want you to split a little bit down the center and then straight across like a half. Okay? This would be considered uniform if this was 33.3 repeated percent. This is 33.3 repeated percent, and this is 33.3 repeated percent. Okay? That would mean that it has an equal split. Versus here, this is non-uniform. With non-uniform, you have 1 or more outcomes that are different probabilities than the rest. So actually, you know what, and right down here, we're going to go ahead and split this way. Okay, let's say that this is 12%, this is 13%, this is 25%, this is 50%. Okay, so in a situation like that, they all have a different probability of occurring. So if I were to spin this spinner, and let's say that this 50% was red, I'm more likely to land on red each time than I am to land on any of the other colors. Versus here with a uniform one, you have the same chance of landing on all 3 colors. Okay, all 3 colors have the exact same probability or an equal opportunity to be chosen. All right? Okay, go ahead and flip it over back to your original. So taking a look here, if I wanted to go ahead and draw out my spinner, I have a 3-section spinner, and I know that they are going to be labeled red, which I don't really have a red, so I'm just going to highlight it pink. Okay. I have a green, and I have blue. Those were the colors that they were identifying on there. And I know that those are the colors because if I lead my little chart, that's what it says. Okay? So now, what we're doing is we are going to spin the spinner 60 times, and then we're going to identify how many times we landed on a green, how many times we landed on a blue, how many times we landed on a red, and we're going to document it inside of our graph. So this portion right here, this table of information, that's the experimental portion. When we are calculating experimental probability, we are using this table because it is actual results. So there was action that occurred. We did this 60 times, okay? And we know it's 60 times because we can add up all the times that we landed on each of the colors. So 21 and 15 and 24, when we add those together, it's going to come out to 60. But also in the problem, it says that it happened 60 times. That's the 60 trials. That's your experiment. You're performing something. Now, the portion right here where it says that you have a spinner with the 3 equal sections, that portion right there is telling you what the experiment looks like. That's where you get your theoretical off of. The actual item and not the results. Okay? So for your theoretical probability, you're going to go ahead and focus on just the spinner. Not the trials. You're focusing on the actual spinner and not the trials. So there's our actual spinner. So theoretically, I'm going to abbreviate theoretical, the probability that we would land on red, which is what they're asking, is 1 out of 3 times. Okay? Now don't forget that if you wanted to convert that into a decimal, then all you would have to do is take 1 and divide it by 3, and that would come out to 0.333, and it just keeps going. And if you wanted to calculate that as a percentage, you would just take the decimal, 0.333, and multiply it by 100, and that would come out to 33.3% repeated. Okay? So you have a fraction answer, you have a decimal answer, you have a percentage answer. It's good to know how to do it in all 3 forms because you do not know which form is going to be given to you. So you should know it in all 3 forms. Okay? For the second part, we're finding the experimental probability of landing on red. So again, with the experimental probability, you need to look at the actual action, the trials. Okay, so that's where you're going to use your table of information. So for our experimental probability of landing on red, red occurred 24 times. So if I'm looking at my table goes up to 24 for my red. So I have 24 times out of the 60 total trials. Okay, how many times did I actually land on red out of the total number of trials that we had? And that's going to come out to 2/5. We would simplify that to 2/5. Changing it to a decimal would be 0.4. Changing it to a percent would be 40%. You want, again, to know it in all forms. Okay? So now we can make a comparison to the two. Comparing our experimental probability to our theoretical probability, are they the same? No. They're off a little bit, aren't they? In fact, our experimental probability, which was 40%, is going to be greater than our theoretical probability, which was about 33%. So we're making those comparisons. Okay, I want you guys to try problem number 2 on your own. Identify your theoretical probability of rolling a 6. Identify the experimental probability of rolling at 6, and then go ahead and compare the 2 probabilities. Okay, looking here, who can tell me what's the theoretical probability of rolling a 6, Mason?
1/6 equals 16.6.
Okay, percent, right? Okay, so again, for our theoretical probability, we're focusing on not the tally table, but we're going to actually focus on the number cube. So I'm just going to draw a quick number cube. You don't have to draw one, but I'm just letting you guys know that this is what it's going to be. So like if we have this, and it might be like 1, 2, 3 here. Like, so there we've got our little number cube. Okay, so we want the probability in theory that we're going to land on a number 6. Well, the number 6 only happens 1 out of 6 times, which if you were to go ahead and convert that into your decimal, you'd have 0.16 repeated, which is going to be roughly about 16.7%. Okay? Or 16.67% or 16.667%, depending on what it asks you to round it to. Okay? Now, theoretical probability, with your theoretical probability, that's where the action is going to be needed, which is what your tally table is. Okay, so this is your experiment. So what's the experimental probability that we are going to roll the number 6? Kingsley.
12/32
Okay, now don't forget 12/32 can be simplified. So if you were to put your answer as 12/32, you'd get marked wrong. Okay, so you need to make sure you simplify it. What's the fraction in simplest form, Aaron? 3/8. Okay, so yes, we do know that the 6 is going to occur 12 times. In fact, the number 1 occurred 7 times. This number 2 occurred 3 times. The number 3 occurred 3 times. The number 4 occurred 5 times. The 5 occurred twice. And then the 6 occurred 12 times. So we have 12 out of a total of 32 trials. Okay, there was a total of 32 trials, which would simplify to 3/8, which is 0.375, which is 37.5%. Okay, so there's our experimental probability. And then making that comparison. So our comparison for experimental being 37.5%, it is greater than what the theoretical probability was of 16.7%. Okay? All right, let's go ahead and flip it on over to the next page. For here, I went ahead and created a table for you showcasing what it would look like if you were rolling two different two dice, different colors. They have a very specific set of outcomes. In fact, there's a total of 36 different outcomes, because each time one die lands on a 1, the other die could land on a 1, or it could land on a 2, or a 3, or it could land on a 4, or a 5, or a 6. So there's 6 different ways that the second die can land while the first die stays stagnant. And then if the first die changes, then there's 6 different ways that it can go where the first die is a 2. There's 6 different ways that it can go where the first die is a 3, and so on and so forth. So I've listed out for you, boys, I've listed out for you the different possible outcomes that could happen where red lands on a 1, but green changes. Or where red lands on a 2, but green is the one that changes, and so on and so forth. What I want you guys to do is, based off of what they've landed on, identify the sums that we have. So go ahead and fill out this chart by identifying the sum of our results. So what I mean is, if both of them land on a 1, what's the sum? 2. Because you had added them together, right? Go ahead and fill that in. Quiet. Let's go over this real quickly, taking a look here at our sums. Shh. Caden, hush. Taking a look at our sums that we've got provided. So if they both land on a 1, then the sum is going to be a 2. If we have a 1, 2, the sum's a 3, and then it keeps going 4, 5, 6, and 7. And when we go over to our next column, we've got 3, 4, 5, 6, 7, 8. Next column, we've got 4, 5, 6, 7, 8, and 9. Next column over, we have 5, 6, 7, 8, 9, 10. Next one we have 6, 7, 8, 9, 10, 11. And then the last one is 7, 8, 9, 10, 11, and 12. So these are the different kinds of sums that we could provide. Obviously, there are some sums that are going to repeat, which is perfectly fine. So what we're going to do is we are going to calculate the theoretical probability that the sum is going to be greater than or equal to 8. We're going to check out to find a sum that is greater than or equal to 8. Okay, and it's theoretical, so have I done any experiment yet? No, have not done any kind of experiment yet. So I want a sum that is greater than or equal to 8. So I'm going to go through and identify every one of the sums that's greater than or equal to 8. So here's one of them. If I land on a 2 and then a 6, I get an 8. If I land on a 3 and then a 5, or a 3 and a 6, those are greater than or equal to 8. If I land on a 4, 4, a 4, 5, or a 4, 6, those would qualify. If I land on a 5, 3, a 5, 4, a 5, 5, or a 5, 6, those are going to qualify. And then 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6 will all qualify. So how many outcomes qualify for being greater than or equal to 8? Eager. 15. Shh. Out of how many total outcomes do we have here? Matthew. 36. Shh. So all we have to do is then simplify this. They're both divisible by 3. That would give us 5 out of 12. If we simplify it as a decimal, that would be about 0.417. As a percentage, that would be 41.7%. Okay? So here's our theoretical probability that we're going to get a sum greater than or equal to 8. Okay, now, the experiment portion. So what we're going to do is I'm going to go ahead and roll. I'm going to roll these two different dice. I know I said red and green, but my green die is gone. I don't know where it went. So we'll calculate it as red and yellow instead. So I'm going to roll them. We're going to identify what the rolls landed on and what the sum would be. And we're going to do this for 10 trials. We're going to do it for 10 different trials. Okay, so the first time I get a 5 and a 5. Thank you. Okay, so I'm going to write down that I landed on a 5 and a 5, which is going to give me a 10. Okay, then we're going to do it again. Shh. We have a 2 and a 3. So the red 3 and the green 2. I know, I just told you. Did you not listen? I said my green die went gone, so we're going to pretend this is green. Okay, doing it again. Shh. We get 3, 3. So we have a oops. Wrote this in the wrong spot, sorry. This is a sum of 5. What's 3 and 3 going to give us? 6. All right, we're going to do it again. Shh. We get a 5 and a 3. What's 5 and 3? 8. Some of you having little side conversations needs to stop. Okay, we've got a 4 and a 2. What is that going to give us a sum of? Okay. We have another 4 and a 2. So again, 6. All right. We've got a 5 and a 3. So we have a 5 and a 3, which is going to give us 8. Okay. We have a 6 and an 11. I mean, a 6 and a 5, that's an 11. 6 and 5, which is going to give us 11. We have a 3 and a 6. Gives us 9. Oops. Wrong color. And then we have a 4 and a 6. So 4 and 6 is 10. All right, now we want to go ahead and calculate what the experimental probability was. So with the experimental probability, we're now calculating how many times we actually did land on a sum that was greater than or equal to 8. So our first roll satisfies our condition. Our fourth roll satisfies the condition. Our seventh roll satisfies the condition. Our eighth roll, our ninth roll, and our 10th roll. So how many times did we satisfy the condition? 6. So the probability that we actually landed on a sum that was greater than or equal to 8 was 6 times out of how many trials? 10 out of 10 trials. So that was 3/5, which is going to come out to 0.6, which is going to come out to 60%. Okay, so question for you. Is our experimental the same thing as our theoretical? No. So what I want to know is what could we potentially do in order to get our experimental probability to be as close as possible to our theoretical? So what do you think? Roll the dice more times. So the more times that you perform your experiment, eventually it's going to get closer and closer to your theoretical. Okay? So like I said before, think of theoretical as the correct answer. That's the goal that we want to achieve. Your experimental probability is the process of getting there. The more times you perform the experiment, the closer the results will start to become. Okay, so write that part down. The more trials that you perform, the closer. Do you have to repeat everything I'm saying? It's annoying. Don't be annoying. Okay. The closer the experimental probability will become to the theoretical. Your goal is to try and get as close to theoretical probability as you potentially can. That's what our purpose is. That's the whole reason that we perform the experiments over and over and over again, is we are trying to get as close as possible to that theoretical probability. Okay?